Okay, let's unpack this. Welcome to the deep dive. Today, we're taking a pretty massive detour from the usual talk about lap times and aero. We are strapping ourselves in and going deep into the world of high voltage safety engineering. Specifically, we're looking at how to design a truly bulletproof HV safety architecture for a Formula Student electric car.
And it's so critical. I mean, if the powertrain is the heart of an FSE car, this safety system, what the rules call subsystem 11.0, that's the absolute bottom line. It's what dictates if your car even gets to compete. And more importantly, if your driver stays safe.
Exactly. We're working from a strategic engineering requirements specification today, an SOR. It's essentially a blueprint put together by top powertrain architects to guide a new university team. Our mission is to take these dense, sometimes really ambiguous FSG 225/2020-26 rules and break them down. We're going to use the McKinsey MECE framework that's mutually exclusive, collectively exhaustive, and turn them into rock-solid, actionable engineering specs that guarantee not just compliance, but, world-class safety.
What's fascinating here is the strategic context. When you look at new electric teams, the data is just sobering. Something like 40% of them fail to pass electrical scrutineering. They're out before they even turn a wheel in practice.
40%, that's a huge number.
It is. And the failure is almost never about speed or power. It's about poor systems integration, cutting corners on cheap components, and frankly, a deep misunderstanding of the engineering logic behind the rules.
They're just ticking boxes instead of thinking about the system as a whole.
Exactly. So we approach this not as a checklist, but as a risk mitigation strategy. Our SOR, this whole framework, it has three core goals. First, zero compromise personnel safety. That means preventing shock, arc flash, thermal runaway, the big stuff.
Okay.
Second, maximizing your scrutineering pass rate through what we call visual compliance.
What do you mean by that, visual compliance?
It means designing a system that's so clear, so robustly logical, that the judges can look at it and understand it immediately. They don't need a nervous student to give them a 30-minute explanation. It saves a huge amount of time and stress.
It sells itself, essentially.
It sells itself. And third, dynamic system robustness. Look, you're building a race car. It vibrates, it pulls G's, it hits curbs. Your safety systems have to be hardened against nuisance tripping in those high vibration, high G environments.
That's a massive point. I mean, you can follow every rule to the letter, but if your shutdown circuit trips every time the driver brakes hard, your car is basically useless
Yeah.
and dangerous.
You're designing for resilience, not just rulebook compliance. And the key constraint, the thing driving all the latest rule changes, is this shift away from, let's say, vague measurements and toward what we call real physical state monitoring. The rules now demand proof of the mechanical state of things, forcing you to rely on hardwired feedback, not software assumptions.
Okay, so let's start there with that evolving regulatory context. You're saying the big strategic shift is the pressure moving entirely onto the electrical system form, the ESF.
That's right. The old EAR, the Electrical Accessibility Inspection Report, that's pretty much obsolete now. For years, teams kind of built the car and then documented it after the fact.
Can't do that anymore.
Not at all. The entire burden of proof is now on the ESF. You have to provide 100% logic verification on paper before you even think about manufacturing. If you can't define your safety logic in that document, the Rules Committee just assumes you haven't engineered it properly. You're rejected on the spot.
That sounds like a huge culture shock for a lot of teams. It's forcing a front-loaded engineering discipline.
It forces strategic thinking from day one. This SRR we're talking about is basically the blueprint for filling out that ESF with logic that is verifiable and, MEC compliant. No more hand-waving.
So let's dive into a specific rule change that really shows this. Battery temperature monitoring, EV 5.8. It sounds simple, but you're saying the new wording is a game changer.
It's a perfect case study. The rule is now incredibly rigorous. It states that your temperature sensors must have direct physical contact with either the cell's negative terminal or its main bus bar.
So you can't just, glue a thermistor to the side of the cell's plastic wrapper anymore?
That's exactly it. That's no longer acceptable. Placing it in the air gap or on the wrapper is out. It has to be in direct thermal communication with the conductor.
Why is that so critical? What's the failure mode they're trying to prevent with that specific requirement?
If you're only monitoring the wrapper, you're getting surface temperature. That lags way behind the core temperature of the cell, especially during a high discharge event. Thermal runaway, the catastrophic failure, it usually starts deep inside the cell or at a high resistance spot weld on the terminal. By the time the wrapper gets hot, it's often way too late.
I see.
By forcing you to measure at the terminal or the bus bar, the rules are putting the sensor closer to the highest current path. It gives you a much faster, much more accurate prediction of internal heating before it's irreversible.
So the key takeaway for a new team is what? Mechanical integration.
100%. The temperature monitoring PCB, the little board with all the sensors, it has to be a fundamental part of the module's mechanical design from the very beginning. If you try to retrofit sensors onto your bus bars after the module is all sealed and bonded together, you're going to compromise your creepage and clearance distances. It's a structural and electrical disaster just waiting to happen.
The mechanical team has to be designing pockets and standoffs for the electrical sensors before they even make the first weld.
They're inseparable. And then you have the technical requirements. You need to cover at least 30% of your cells, but even more critically, you have to maintain isolation. These sensors are touching high voltage, so they have to respect that isolation barrier. That means either you have a really clever mechanical design with proper creepage, or, more realistically, you use isolated temperature acquisition chips.
Right, something that physically separates the high voltage side from your low voltage control circuits.
It's all about reducing the time to failure detection. Faster, more accurate temp data gives the BMS more time to trigger a shutdown before you have a fire.
Makes sense. Okay, let's move to another foundational concept that touches every single safety sensor. System critical signals, or SCS, that's rule T11.9.
Right. SCS is the rule that demands diagnostic coverage. It says that any sensor whose failure could affect the shutdown circuit, so your throttle, your brake pressure, your TSAL voltage measurement, it has to have both open circuit detection and short-to-ground detection.
And this immediately makes using simple on-off mechanical switches a really bad idea, right?
A very bad idea. A standard switch is just binary, on or off. If the wire from that switch breaks, it looks like an open circuit. But if the switch is already in its safe position, which is also open,
the broken wire looks identical to the safe state. The system has no idea there's a fault.
and that is a classic dangerous failure. It hides the fault. The strategy is to move away from that and use analog voltage signals, your typical 0 to 5 volt industrial transducers.
And then you pair those with something called window comparators. Let's unpack that. Why a window comparator, not just a single one?
A single comparator just tells you if a signal is above or below one threshold. A window comparator defines an acceptable operating range. For a 5-volt sensor, that's typically between, say, 0.5 volts and 4.5 volts. It actually uses two comparators.
Okay.
Comparator A checks the lower bound, is the signal above 0.5 volts. If it drops below that, you've probably got a broken wire, an open circuit fault.
Okay.
Comparator B checks the upper bound. Is it below 4.5 volts? If it goes above that, you've got a sensor saturation or maybe a short to power fault.
So you're creating this invalid state outside of the normal operating window. If the signal is too low or too high, the system knows the sensor itself is broken, regardless of what it's trying to measure.
Exactly. That's the diagnostic coverage T11.9 demands. It's the difference between a simple circuit and a robust industrial-grade one that constantly checks its own health.
Okay, before we get into the specific subsystems, let's just nail down this concept of the isolation barrier. It seems to underpin everything.
It does. So you have two electrical domains in the car. GLV is your grounded low-voltage system, 12 or 24 volts, grounded to the chassis, running all your control electronics. Then you have TS, the tractive system. That's anything over 60 volts DC, and it must be non-grounded or floating. That's your first line of defense.
And the isolation barrier is the boundary between them.
It's the physical and electrical boundary. Conceptually, it's the line between life and death. Every high-voltage component's enclosure has to be grounded, but the conductors inside have to be isolated from that enclosure.
And if data needs to cross that barrier,
No direct metallic path, ever. Data has to use optocouplers, which use light, or digital isolators. If you need to send power across, you must use an isolated DC-DC converter.
and it's not just about safety from shock, it's also about noise, right?
A huge part of it is noise. The inverter is switching massive currents, creating huge electromagnetic interference, or EMI. That isolation barrier and using components that can reject that noise is what keeps your low-voltage control system from going haywire.
Okay, that's a great foundation. Let's move into the first big subsystem, the TSAL, the tractive system active light. That blinking red or solid green light that's the ultimate source of truth.
And the absolute core constraint here, the non-negotiable principle, is that the TSAL's core logic must be hardwired. No microcontrollers.
Why is that so strict?
Because if your main vehicle computer, the VCU, crashes, or you load some bad code, the TSAL has to keep working. It must be pure, robust, non-programmable analog or discrete logic. It has to be fail-safe.
So let's break down its two states. It's a mutually exclusive system based on real physical measurements.
Right. The safe state is a solid green light. And to get that, you need a triple confirmation. The low voltage master switch must be on, and the attractive system voltage must be below 60 volts, and all the main contactors, the ARs, must be mechanically confirmed it's open.
All three.
All three. If even one isn't true, the green light has to go out.
And the other state, the active state, is a flashing red light. That takes priority over everything.
Absolute priority. It has to flash between 2 and 5 hertz if high voltage is detected anywhere, or if the contactors are closed.
Let's deep dive on that red light logic first. That's the immediate hazard alert.
And the first rule is independence. The detection circuit for the red light has to be completely separate from the green light circuit. A single sensor failure can't be allowed to mask a high voltage state.
Okay, and where do you have to measure that voltage? You said the location is very specific.
It has to be the DC link capacitor. That's the big capacitor bank right at the input of the motor inverter.
Why there, and not just at the battery?
Because those capacitors can hold a lethal charge for minutes after you disconnect the battery. If you only measure at the battery, you could open the contactors, think the system is safe, but there's still 600 volts sitting in the inverter. The red light has to monitor the DC link to warn people about that residual energy.
Okay, that makes perfect sense. So let's talk about the circuit itself. How do you build this?
Okay, first step is the voltage divider. You have to take that 600 volts and safely knock it down to something a 5-volt circuit can read. We use high-precision, high-tolerance resistors. And the critical design choice is to use a chain of multiple resistors in series, maybe 600 kilo-ohm resistors instead of one big 600K one.
Let me push back on that, because some might say a single high-quality component is simpler. Why the complexity of 6?
It's a great question, but it's a dangerous simplification. With a single resistor, the full 600-volt potential is dropped across that one tiny component. The thermal and voltage stress is immense. If it fails open, your low-voltage circuit is suddenly hit with the full 600 volts.
Catastrophic failure.
Complete catastrophe. By using a series chain, you divide the voltage and the heat across multiple components. The stress on any single one is dramatically lower, and the redundancy is much, much higher.
Okay, so you've divided the voltage down. What's next?
That low-voltage signal goes into an automotive-grade comparator, like an LM2903. It compares that signal to a very stable reference voltage that represents 60 volts. The moment the system goes over 60, that comparator flips.
And then you have to get that signal across the oscillation barrier.
Right, and this is where noise immunity is key. The comparator's output is referenced to the high-voltage ground. So to cross the barrier, you have to use a high CMTI optocoupler.
High CMTI, common mode transient immunity. Why is that specific rating so important? Why not just a generic opto?
We're fighting the incredible electrical noise from the inverter. It's switching hundreds of amps at high frequency, which creates huge noise spikes. A standard optocoupler can't handle that. The noise will bleed across the barrier and corrupt your low-voltage logic.
Causing the light to flicker, or worse, causing a nuisance trip of the whole car.
Exactly. The high CMTI rating ensures the isolation holds up even in that incredibly noisy environment.
Okay, so you have an isolated, clean signal on the low-voltage side. How do you make it flash?
You use the most reliable, non-programmable oscillator ever made, the 555 timer. You configure it as an astable multi-vibrator. The signal from the optocoupler just enables the 555, and it generates that perfect 2 to 5 hertz square wave for the flashing light. It's simple, deterministic, and bulletproof.
Incredible. So much engineering in one simple light. Okay, what about the green light logic? This is about proving safety.
It is. And it relies on two main inputs. First, you have to monitor the mechanical state of the main contactors using their built-in auxiliary contacts. This confirms the physical path is open.
And this is where the SCS rule forces a really important design choice. The recommendation is to use normally closed or NC auxiliary contacts. Walk us through why normally open is a bad idea.
Let's think about the fault. The safe state for a contactor is when it's de-energized or open.
Right.
If you use a normally open NO contact, when the contactor is safely open, the NO contact is also open. Now, if the wire from that contact breaks, what does the logic see?
An open circuit.
An open circuit, which looks identical to the safe state. So the system is blind to a broken wire. That's a dangerous failure.
Okay, so how does normally closed fix that?
With a normally closed NC contact, when the contactor is safely open, the NC contact is closed, completing the circuit. The logic sees a continuous signal. If the wire breaks, that signal disappears. The logic sees an open circuit, knows immediately there's a fault, and kills the green light. It allows for wire integrity checks.
It's fail-safe. Okay, so that's the first input. What's the second
The
one?
second is a redundant voltage measurement, but this one is taken on the battery side of the main contactors.
And what failure is that specifically designed to catch?
Contactor welding. The main power contacts can literally weld themselves shut from a massive current spike, even if the coil is de-energized and the auxiliary contacts say everything is open.
Ah, so you have a contradiction. The auxiliaries say open, but there's still voltage.
Exactly. A catastrophic contradiction. And when that happens, it has to trigger the latching mechanism. The green light is forced off and locked off. You can't just flip a switch to fix it.
It forces a full power cycle of the low-voltage master switch.
Right. It forces the team to physically investigate and clear the hazard, the stuck contactor, before the system is allowed to even try to enter a safe state again. It's all about engineering discipline.
Okay, let's move on to what you called the silent digital guardian, the IMD, or insulation monitoring device.
The IMD is the firewall between your high-voltage system and the chassis. Its job is to constantly monitor for insulation breakdown, for ground leakage. It's there to find the first fault so you can shut down before a second fault creates a dangerous short circuit.
And for FSE, the standard is pretty much one device, right?
Yeah, you don't build this yourself. You use the Bender isometer IR155. It's the industry standard designed specifically for EVs.
What's the trigger threshold we're working with?
The shutdown has to happen if the insulation resistance drops below 500 ohms per volt, and it has to happen within 20 seconds. So for a typical 600-volt system, that's a 300 kilo ohm threshold.
And the challenge isn't the device itself, it's decoding what it's telling you. It puts out a PWM signal, not just a simple on or off.
Correct. And relying on its simple status OK pin isn't good enough. World-class teams decode the full PWM signal from the measurement output. The frequency of that signal is the data. So 10 hertz is normal. 20 hertz might mean under voltage. But the critical ones are 40 hertz, which means the IMD itself has an error, and 50 hertz, which means you have an earth fault, your insulation is compromised. Both of those have to trigger an immediate shutdown.
So again, no MCU allowed. How do you reliably tell the difference between 10 hertz and 50 hertz with just hardwired logic?
You use a specialized analog chip called a frequency-to-voltage converter, or FVC. The LM2917 is a classic example. It takes that PWM frequency in and outputs a smooth, proportional DC voltage.
So 10 hertz might become 1 volt, 40 hertz becomes 4 volts, and so on.
Exactly. Then you just use a simple analog comparator. If the voltage from the FVC suddenly jumps above, say, 3.5 volts, the comparator flips, and that triggers your latched shutdown circuit.
What's the advantage of that over some other method, like a digital counter?
It's about analog robustness. The FVC is designed to handle noisy inputs from an automotive environment and give you a stable DC output. It's also great for diagnostics. If the IMD signal wire breaks, the frequency goes to 0, the FVC output goes to 0 volts, and you can detect that as a fatal device error too.
It's a much higher level of fault detection. I know there's also a very specific rule about how the IMD itself is grounded.
Yes, its own grounding integrity is critical. The Bender requires its power ground and its measurement ground to be connected separately back to the chassis start point. This allows it to detect if its own ground connection is broken, which is another failure mode that has to be caught.
And just like the TSAL, if an IMD fault happens, it has to be indicated and latched.
Mandatory red IMD light in the cockpit for the driver.
Yeah.
And yes, the fault has to latch. You must do a full power cycle of the LVMS to reset it, forcing the team to find and fix the insulation breach. Okay, let's shift gears to the other analog watchdog. The BSPD, the brake system plausibility device. This is the last resort for an uncontrolled acceleration event.
The BSPD is your non-programmable failsafe. It's there for that terrifying scenario where the throttle is stuck open or the VCU has gone rogue, but the driver is hard on the brakes.
So what are the strict trigger conditions for it to intervene?
There are two, and both have to be met at the same time. Condition 1 is hard braking, which is usually defined as more than about 30 bar of pressure in the brake lines. Condition 2 is high power output. The rules say you can use throttle position, but for an EV, it's much better to monitor current. We use a 5 kilowatt power threshold.
And you calculate the trip current based on the minimum battery voltage, right?
Exactly. So iTrip equals 5,000 watts divided by Vmin. That makes sure the system is equally sensitive whether the battery is fully charged or nearly empty. And the most important part, both of these conditions have to be sustained for more than 500 milliseconds.
That half-second delay is everything. Drivers often overlap the brake and throttle for a moment during aggressive driving. Without that delay, the car would be shutting down all the time. 500 milliseconds is long enough to filter out those transient inputs, but short enough to intervene quickly in a real failure.
So how do you build this analog computer to do all this without a microcontroller?
It comes down to really careful component selection. For the inputs, you're using industrial pressure transducers and Hall-effect current sensors. And because they're system-critical signals, they first have to go through their own window comparators for fault detection.
Okay, so you have clean, validated signals for brake pressure and current.
Right. Those signals then feed into an analog AND gate. The output of the AND gate only goes high when both conditions, hard braking and high power, are met.
And that output starts the timer. Let's focus on that RC delay circuit. How do you guarantee a precise 500 millisecond delay?
This is a true test of engineering discipline.
Yeah.
You can't use cheap parts. For the capacitor, you must use a low-leakage tantalum capacitor. A standard ceramic one will leak current and your timing will drift all over the place.
And the resistor.
Has to be a 1% or better precision metal film resistor. If your component values drift with temperature, your timing is shot. The A&D gate output slowly charges this precision RC network. After 500 milliseconds, the capacitor voltage hits a threshold on a final comparator.
Which then drives a latch.
Exactly. An SR latch or an SCR that locks the shutdown circuit open, power is cut and stays cut.
And again, you're recommending the manual power cycle reset, not the 10-second auto reset the rules sometimes allow.
Always. An auto reset is dangerous. A BSPD trip means something went catastrophically wrong with your control system. You need to force a full reboot and diagnostic check, not just let the driver keep going.
Going back to that visual compliance goal, how do you make this circuit easy for a scrutineer to test?
You build in dedicated test buttons. It's non-negotiable. The board must have 2 buttons that let a scrutineer artificially trigger the brake and power signals. They can press both, hook up an oscilloscope, and verify right there that the shutdown happens at exactly 500 milliseconds and that it latches. It turns an hour-long inspection into a 5-minute check. So now we need to shift from, the logic to the physical world, the actual infrastructure that has to hold up under racing conditions.
Right, the structural and electromechanical integrity. Let's start with the HVIL, the high voltage interlock loop. You called it the vehicle's nervous system.
That's what it is. It's a simple, low-voltage serial current loop, a daisy chain that physically runs through every single high-voltage lid, cover, the MSD, and every single HV connector. If that loop is broken at any point, it means something is open or unsecured, and it must immediately open the shutdown circuit.
And the real genius here is in the connector technology itself, the last mate first break design. This prevents a truly terrifying event.
It prevents arc flash. An arc flash is when high voltage current jumps through the air, creating a plasma explosion that's thousands of degrees. It can cause horrific burns and ignite fires.
So how does the connector stop that?
Good automotive HV connectors have 2 small, shorted signal pins for the HVIL right alongside the big power terminals. When you plug it in, the power terminals make contact first and the HVIL pins connect last. But when you unplug it, the HVIL pins break contact first. This instantly opens the shutdown circuit and kills power to the main contactors before the high voltage terminals have physically separated enough to draw an arc. It's a preemptive cut.
And if a team tries to use cheap industrial connectors without that feature,
They will fail scrutineering, period. The inspectors will do a live unplug test. If power isn't cut before those terminals separate, the car is deemed unsafe and you're done.
and the control for the HVIL has to be hardwired, no software in the loop.
Absolutely. The HVIL loop itself must physically cut power to the contactor coils. The VCU can monitor it for logging and diagnostics, but the execution has to be physical.
Okay, let's talk about the energy gatekeepers themselves. The contactors, or ARs, and the main fuse.
When you're selecting a contactor, everyone looks at the continuous current rating. But the spec that really matters is the braking capacity.
Which is what, exactly?
It's the ability of the contactor to interrupt a massive short-circuit current. We're talking thousands of amps, without welding itself shut. A lithium battery can deliver incredible fault current. If your contactor isn't rated to break that, the contacts will just melt together and your shutdown circuit becomes useless.
You also mentioned a feature called an economizer.
Yes, this is a strong strategic recommendation. Contactors need a big pulse of current to close, but much less current to stay closed. An economizer circuit uses PWM to reduce the holding current. This saves a huge amount of power from your low-voltage battery, which is critical during a long race.
And of course, they have to be normally open.
Always. So if you lose all LV power, they fail into the safe, open state.
Now, fusing, the rules are very specific here.
The fuse goes on the HE positive line. and it has to be physically inside the accumulator container. But the absolute most critical rule is you must use an EV-specific DC fuse,
Let's really hammer this home. Why are AC fuses so strictly forbidden?
because they design completely differently. An AC fuse relies on the current crossing 0 volts, 100 or 120 times a second to help extinguish the arc when it blows.
A zero crossing that never happens in a DC system.
Never. So if you try to interrupt high voltage DC with an AC fuse, the arc inside it will never extinguish. It will just sustain itself, destroying the fuse, melting everything around it, and failing to stop the current. It's one of the most dangerous mistakes a team can make.
And the rating logic is crucial too. The fuse protects the cable, not the battery.
Correct. So the fuse amperage rating has to be less than the cable's rating, and its interrupt rating has to be higher than the battery's maximum short circuit current.
Okay, last piece of this section. The manual service disconnect, or MSD.
The MSD is the big physical kill switch. Its job is to break the middle of the battery pack to divide the voltage down to a safer level for maintenance. Mechanically, it has to be tool-free, colored orange, and within the roll hoop envelope. But critically, the handle itself has to be part of the HVIL loop. When you pull that handle, the HVIL must break first, killing power before the HV terminals separate.
Okay, let's move to the last physical parts. Wiring, shielding, and the firewall.
The wiring rules are straightforward. All HV cables must be orange. They must use 360-degree shielding, and they have to be strain relieved to pass a 200-Newton pull test.
And the shielding needs to be grounded properly to control all that EMI we talked about.
Exactly. And the strategy here is single-point grounding. You want to tie all your shields back to one central point on the chassis, usually near the inverter, using 360-degree crimp rings.
Why is single-point grounding so important? What are you avoiding?
You're avoiding ground loops. If you have multiple ground paths, you can get these circulating currents flowing through your shields and chassis. Those currents create a ton of electrical noise, which can cause nuisance trips in your sensitive safety circuits. Single-point grounding eliminates those loops.
And finally, the firewall, the driver's last line of defense.
Its job is to give the driver 5 seconds to get out if there's a fire or an electrical failure behind them. It has to block heat, flame, and any sprayed liquid.
And it has to be a specific composite structure, not just a single sheet of something.
Right, it's a layered defense. On the high voltage side, you need a metal layer, at least 0.5 millimeter of aluminum. That's a heat barrier and also a fault path. On the driver's side, you need a rigid, non-carbon fiber material that meets the UL94 V0 self-extinguishing standard. That means if you set it on fire, it stops burning within 10 seconds and doesn't drip. Polycarbonate or Nomex are good choices.
There's also a really strict grounding test for that aluminum layer. The resistance has to be less than 100 million ohms. Why so incredibly low?
It's all about providing a low impedance fault path. If an HV cable fails and touches that plate, you want the current to have an immediate, easy pass to ground. That ensures a massive current spike that will blow the main fuse instantly. If the resistance was high, it could just sit there and generate heat, melting the aluminum or igniting the other layer.
And any wires passing through that firewall need special treatment.
You must use compliant, fire-rated sealing glands. You can't just drill a hole. Those glands maintain the integrity of the barrier against flame and liquid spray.
So after all that incredible detail, what does this mean for a new team? How do you even start? You've laid out a 4-phase roadmap for this.
Yeah, this is the project management that makes it possible. It's all about solving the hardest problems and validating your logic early. So phase 1 is architecture and simulation, months 1 to 3. The only output is your draft electrical system form, your ESF. You're on the computer using SPICE software to simulate your BSPD delay circuit, your TSAL dividers. You're proving the physics works on paper first.
Then you move from the virtual to the physical.
Phase 2, prototype validation, months 4 to 6. You build what we call a safety box prototype, a physical board with your actual hardwired TSAL, BSPD, and IMD circuits on it. And you must use an oscilloscope. You have to physically verify that 500 millisecond delay. You have to verify the IMD triggers at the right frequency. If you can't prove it on the bench, you'll never pass scrutineering.
Phase 3 is when it all goes in the car.
Phase 3, integration wiring, months 7 to 9. This is all about physical integrity. You maintain strict separation, at least 100 millimeters between your HV and LV wiring to prevent noise, and you install and test the full HVIL circuit, making sure it cuts power correctly.
And the final phase is basically becoming your own worst critic.
Phase 4 is simulated scrutineering, month 10. You act like the judge. You do rain tests to look for insulation leaks. You inject resistance into the IMD circuit to verify the trip point. You simulate broken sensor wires and make sure the window comparators catch them. You have to prove reliable cutoff for every single failure mode you can think of. Then you take all that data, all those oscilloscope traces, and put them in your final ESF document.
So the core philosophy is really about discipline.
It is. This whole subsystem is a demonstration of engineering discipline.
Mm.
It's not about being clever. It's about using validated industrial-grade components and rigorously sticking to proven analog logic.
Mm-hmm.
I mean, at the end of the day, race performance wins races. But electrical safety is the license that allows you to compete in the first place. If you neglect this, you're not building a race car, you're building a very expensive paperweight.
That's the perfect way to put it. We've gone from these high-level rules all the way down to specific capacitor leakage rates. The level of detail required is just phenomenal. And it seems like the big trend, especially with that battery temperature rule, is forcing this complete fusion of mechanical and electrical design. The two teams can't just work in their own silos anymore.
They absolutely have to design it as one coherent system from day one.
Which leads to a final provocative thought for you to think about. If the rules now demand physical perf of sensor placement deep inside the battery for thermal safety, where do we go next? We've done a lot to protect against internal electrical failure, so how might future rules expand this focus? Could they demand deeper sensor integration into the chassis or the suspension to prevent a structural failure, like a broken upright in a crash, from causing an electrical hazard? What's the next safety constraint that will force mechanical and electrical engineers to truly become one team? That's it for this deep dive into high-voltage safety architecture. We hope this roadmap helps you build not just a fast car, but an invincible one. We'll see you next time.